really a great pleasure for me to introduce Dani Bassett from the University of Pennsylvania. What do I say? No introduction needed. I would say a brilliant work along the swath of brain connectivity networks, but also interestingly for me, very broad in terms of complex systems in general, social systems, information systems, and Dani's talk will be about control and control theory. So, Dani, once again, thank you. I know you've been at Brain Connectivity once before, at least once that I remember, in Berlin. I remember in 2010. It's been a while.
One of the early ones, yeah.
One of the early ones. So you know what the special challenge is for our presenters, 15-20 minutes roughly. And then we'll branch out the discussion. So thank you for being here, and over to you.
Great, thank you so much. I'm really excited to be here. So I titled this talk Network Control Theory, What is it? Is it useful, and for what? So I'll definitely address what is it. The is it useful, the answer is going to be sometimes, and the for what, the answer is going to be some things. So what is network control theory? Network control theory is a mathematical framework that determines which perturbations can drive the whole system to a desired state. So here's a simple example of a tiny little network motif that has particular states, x1, x2, x3, x4, and then here's a control input that is injected into x1, and that control input looks like this. It has a time varying signal, and a different control input goes into x2. It has a different control time varying signal. And then what you see on the right-hand side is what happens to the activation state of x1, x2, x3, x4 as we drive the system towards some final state. So this technique of identifying or designing perturbations that would drive a particular state change is typically applied to the study of the power grid, to mechanical systems and robotic systems. But over the last few years, several labs have realized that it can be very useful in thinking about the brain, the control of brain dynamics, either intrinsically or exogenously. So when we take those ideas and frame them in the context of neural systems, we do two things. First, we define a trajectory of the neural system to be the temporal path that the system traverses through diverse states, where a state is defined as the magnitude of neurophysiological activity across brain regions or neural populations or individual neurons, depending on the scale that you're investigating, at a single time point. So controllability of a network then refers to the possibility to manipulate network components to drive the system along that desired trajectory. And that is a set of states culminating in this target state chosen typically for its functional utility. So first, before digging into sort of the details of how to construct a network control framework for a particular neuroscientific question, I wanted to mention the difference between control theory and models of communication. So typically the goals of communication models is to capture the evolution of communication dynamics using dynamical models and to characterize the process of signal propagation, sometimes using graph theoretic or statistical measures. And so I sort of think about this the communication models as moving from time one to time two, thinking how does this pattern of communication change? Whereas the goal of control theory is to say, I know I have a target state that I want to get to. How do I design a perturbation that will get me there? So it's almost the inverse problem. So the goal of control theory is to determine the control strategies that would navigate the system from an initial state to a desired final state. So to give you all a little bit more of an intuition for how this works, I wanted to break it down into the inputs for control theory and the outputs of control theory. So the inputs are, number one, a mapping of the network, and number two, a model of dynamics. So, and we'll get into each of those in a second. For the outputs, it's the design of a perturbation. So I'm going to walk through each of these parts. I will first talk about mapping the network, then I'll talk about models of dynamics, and then I'll talk about the design of the perturbation. In mapping the network, we typically would use something like diffusion tractography in humans at the very large scale. If we're studying macaque or mouse, we would typically use track tracing data that maps out structural connectivity. Or in cellular level circuits, we might use electron microscopy There are some advantages and disadvantages for different network types. So I want to start with structural connectivity, because that is sort of the place where all of the network control applications begin in most systems, particularly in the non-neural systems. So we start with structural connectivity. The advantage there is that it allows the model us to model a physical propagation of signals along white matter tracks. So it's really physically motivated, and that's why we use structural connectivity. That's its advantage. It does have a disadvantage in that it does not allow the propagation through local tissue. So if two regions are kind of physically abutting one another, but don't have a strong white matter track between them, then the structural connectivity would say that nothing could flow between here. But in fact, we know that there can be chemical changes and there can be electrical field changes that would allow propagation through the gray matter tissue that doesn't have to go through white matter. So a solution to that disadvantage is to use what's called a touching matrix in addition to the structural connectivity. And that would allow signals to flow not just along white matter tracks, but also through physically abutting tissues. A second disadvantage of using structural connectivity here is that some states of the brain may privilege the flow of information along some tracks more than others, or in some directions more than others. And so a solution to that disadvantage is to instead use effective connectivity matrices. And they're going to be, excellent as long as the estimates are good. So that's a really nice kind of place to go if you care about context dependence. I'll also just put a quick marker here that you can extend the ideas of network control to multi-layer networks, and that can be particularly useful in the study of neurovasculature systems. So when you have a neural circuit and you also have a vascular circuit on top of it and they're coupled to one another, then you really are asking questions or want to ask questions of multi-layer control. So after talking about the model, or the mapping of the network, I wanted to mention the model of dynamics. Typically, one would begin with the simplest model, which would be the linear time-invariant models. These state that the change in the state of the brain at time t, so the state of the brain is x, at time t is equal to the state of the brain at time t minus 1 times the adjacency matrix, which is going to be, again, probably the structural connectivity matrix to begin. And then plus the control energy, or the control input u as a function of time, times b, which is a matrix, typically with ones along the diagonal that indicate which region actually has control input being injected into it. That tells you about the state x, but in case you don't measure x, you actually measure y, then you write down a function from which you can gather y from x. So this is the simplest version of the model. You can also extend that to linear time varying models, where now A is not a static matrix, it's a time dependent matrix. And so that ratchets sets a little bit further on the dimension of complexity here. And then if we go a little bit further, we can go to nonlinear models, where the change in the brain state is a function of prior brain states and control and time, but not necessarily a linear function. So this is sort of the progression that you would work through as you go through different models. One parenthetical note here I wanted to mention is that I'll be talking a lot about energy, and often what we do is that we state that energy is simply a function of the input u. So we define energy as this integral here from 0 to t of u of t squared times delta t. And the reason that we do that is that in many applications of electrical and electromagnetic stimulation, the cost of control scales quadratically with an input, such as resistive heating within electrical circuits. Now, you probably want to know, what are some advantages and disadvantages of those three kinds of dynamical models: the linear one, the linear time varying one, and the nonlinear one? So if we just stick with the simplest first, the linear time invariant models, these are nice because they are simple enough to provide analytical intuition. So you can really dig into the mathematical formulation and you can gather intuitions about what kinds of topologies would allow control to be easy versus difficult. So the structure of the model is simple enough for that. They are extensively developed, the machinery is, for various kinds of control strategies. So that's nice. You build on a very rich literature. And the third advantage is that it's the first approximation for nonlinear dynamics and is often most accurate in the vicinity of an operating point. So those are kind of some of the strengths here. But As we move then to linear time varying models, what are some of the strengths of going, ratcheting down in complexity there? Well, first, these are very useful for studying context dependent dynamics and for developing and understanding context-specific control strategies, because now you have an adjacency matrix that represents the effective flow of information at that time period, in that time window. And so that allows you to say something about the context of those dynamics and context-specific control. Also, the nice thing is that those approaches can build on well-developed tools for estimating effective connectivity matrices. So using, for example, structural equation modeling or dynamic causal modeling or something like transfer entropy. And then as we go to nonlinear models, these are particularly helpful for lots of things, although there's a lot less machinery developed here. But one of the places where they're really, really helpful is when not all of the state space is available to a system, when there are whole sectors of the state space that are prohibited or not physiologically possible, then the nonlinear models are really effective. And there's some beautiful work by Adelson Motter and Sean Cornelius that I just mentioned one of their papers here in Nature Communication in 2013 that talks about that particular utility of nonlinear models and applies it in some interesting ways. So if you're curious, I highly recommend it. Okay, so then the next question is, as you're facing these three different models, which I've just written down as if they were, you can just write them down and do something with them. Another idea is that you could take data that you have and use that to inform which model you choose. So if you have a lot of data, and particularly stimulation data, where if I perturb this region, this is what happens. If I perturb this region, this is what happens. Then you have some other techniques available to you. For example, you can use what's called systems identification, which is a technique that allows you to take stimulation data and infer the model of dynamics that would explain those responses to perturbations. There are two kinds of these sorts of models. One is called indirect predictive control, and that's where you use the data to fit a relatively low dimensional model, which can then be used inside the control framework. So maybe you use it to fit a linear model, maybe you use it to fit a linear time varying model or something that's nonlinear but in a simple way. Alternatively, Fabio Pasqualetti, who's a control theorist at UC Riverside, who I collaborate with really often, has this beautiful work showing that you can do direct predictive control, which skips the fitting of the model and simply uses the raw data directly inside of the control framework. And so there's some advantages to that approach as well. If you're trying to figure out which of these approaches makes most sense for you and for the data that you have available to you, there's a very nice perspective piece from Krishnan and Pasqualetti on Archive Now, and I believe it's in revision somewhere, where they provide some sort of rules of thumb for which of these approaches might be best given particular scenarios of your data. So that has brought us to, we've done mapping the network, we've done models of dynamics. I'd like to get to the last section, which is outputs. How do we design a perturbation? So I'm going to list a few outputs of NCT. The first, I'm going to go from first and simple to sort of more complicated. The simplest one is the impulse response, which is a system's output when presented with a very brief input signal. And here's an image of what that looks like. Along the y-axis is the activity of a node, and then along the x-axis is time. If we stimulate node I, then we can watch node's I activity increase and then decrease, and then we can watch node J's activity lag node I, and then come up back in activity later and fall away. I will note that for some models of dynamics, such as a linear time invariant one, the impulse response can be solved for analytically, which is nice because it removes the need for simulation and offers greater opportunity for mathematical intuition. The next step in terms of outputs would be a controlled response. So this is not just the response of the system to any input, but the system's response to some controlling input U from some initial state x naught. And U of t can be, it's time varying, first of all, it's not one impulse, and it can be applied to multiple different nodes inside of the network, right? So here's an example where you have a small network and inputs are injected into 3 different spots at different times. So input injected into the peach node happens here and here, input into the blue node happens here and here, and input into the purple node happens here. And so what you can see from these time traces is just the change in activity of each of those regions based on when inputs are placed into different areas. Now, again, for the linear time invariant system, the response, this controlled response, will have two components. The first one will be the impulse response, which we've just described. And then the second will be a convolution of the mapped inputs, which is the B matrix times U, with the impulse response. So it's a nice additive framework and allows you to really understand what's going on very simply. That leads us to the third output of network control theory, which is achieving desired state transitions. From the controlled response, which we just described, we know that we can map the input to the response. That map is known or defined, and one can therefore design a mapped input, BU, to drive a desired response, XT, capital T, where that means sort of final target. And I will note here, because it's going to become important in 2 more slides, that there can be many solutions that drive the desired response. It might not be one, there might be many. And so then you can have the opportunity to decide which kinds of inputs you might want. I'll get to that again in a second. The fourth output of network control theory is controllability. And so that assesses whether or not a system is controllable. A system is controllable if there is a control input that brings our system from an initial state to a final state in finite time. Now, that's a sort of very generic capacity of a system, but you might be interested not in global controllability like that, but in only a subset of initial and final states. And if you care about only a subset of initial and final states that maybe are biologically relevant, then you would study some very specific associated control strategies that are only about those state transitions. 2 examples are the average controllability and modal controllability, and you'll see those in the literature. I just want to frame those as specific control strategies that are for subsets of state transitions. And then the final output is the minimal energy control. So here what you want to do is to design the control input U to minimize the control energy and possibly other factors to drive the desired response. Why do you want to minimize the control energy? Well, because particularly for biological systems, they have a energy minimization constraint. They don't want to exert more energy than they need to. So if we're studying intrinsic capacities, energy minimization is useful and biologically plausible. But also, if we are using this approach to guide stimulation, we don't want to have too much control energy injected into the tissue because that heats the tissue and can cause damage. So those are 2 reasons that we want to minimize the control energy. We also sometimes want to minimize the distance of the current state X from the target state, and that allows a straighter trajectory from your initial state to the final. And that straight trajectory can sort of minimize, the brain moving into very disparate parts of the energy landscape that may not be relevant to it and may also not be beneficial. So now you're probably wondering, how do I know if I made the right choice in mapping the network, in modeling the dynamics, and in choosing the perturbation? And I think, as with all modeling efforts, the answer depends on the scientific question. I try to think about the right choice or a good choice in terms of 3 kinds of validity. You could have descriptive validity of your approach, and for that you would need the network map and or the model of dynamics to match data. If the network map and or the model of dynamics matches data, then you have descriptive validity. You could alternatively have explanatory validity, where the outputs of the control theory correlate with behavior, cognition, and symptoms, and maybe even a step further, the theory provides candidate explanations of mechanism or of cause. And third, you could ask for predictive validity. Does the framework predict the future response of the system to stimulation? And can it predict behavior, cognition, and symptoms? So these are 3 ways to ask this question, I think, in a more rigorous way. So a few recent methodological extensions I wanted to mention is that there is now work from Tomás Manera, where he moves from the control of activity to the control of functional connectivity. And I think that's a really interesting expansion of the approach. We have not used it yet, but I think it's really interesting and exciting. Second, we can separately assess transient versus persistent control strategies, so control over different time scales and control over different spatial scales in the network. And that was work that was led by Evelyn Tang. I really also love this paper from Singleton et al. In 2021, which is on bioRxiv. It just came out. And what they did is that they tuned the B matrix to account for regional variation in serotonin receptor levels. And I think that's such a neat interdigitation between the biological variables that matter for dynamics and the modeling framework. So highly recommend reading that one. And lastly, we can study brain states that are task relevant instead of sort of pulled from thin air. We can use beta weights of a general linear model applied to fMRI, and using those as the brain states allows us to ask question about task transitions or task switching. And that's work led by Urs Braun. The last slide I have for you is this one, which is question spaces that the field is currently tackling. So first, I've been really interested in modeling cognitive control as a network process. For example, using assessments of executive function and dysfunction and understanding its development. Also relevant here are studies of the energy landscape modulation by drug or by placebo that may enhance cognitive control capacities. The second broad umbrella area that people are working in is using network control to better understand the functional consequences of altered brain structure in disease states. So there are some beautiful papers in epilepsy, in bipolar disorder, in schizophrenia doing just that. Also relevant here are assessments of heritability of network control statistics. I think that's beautiful work too. The third broad area is using network control to understand brain dynamics in response to tasks. So for example, rest versus visual processing, working memory. Also, how does brain-computer interface control work? So these are all, how might these control dynamics help us to better understand task performance? Also relevant here are studies probing control energy as a marker of cognitive effort. And the last place where there's significant work right now is using network control to understand brain response to stimulation, like transcranial magnetic stimulation and grid stimulation in epilepsy. But also relevant here are studies designing personalized stimulation paradigms. So with that, I think I made exactly 20 minutes. So I would love to have questions.
Fantastic. Thank you so much, Dani. That was on the spot and very thought-provoking. And indeed, it has provoked many questions that I'm looking at in my Q&A window. I'm going to, I'm organizing these a little in my head as to what's going on. Oh, Randy, you have your hand up. Do you mind, Randy, if I go to one or two of the audience questions first? They came in, some of them quite early in the talk. Matteo Mancini, if you are hearing me in the audience, please raise your hand. There you are, and I will unmute you. Go ahead and ask your question, please.
Hi, thanks for the wonderful talk. I always appreciate a lot hearing about the network control framework because it's really amazing. And as you were talking, I was thinking, is there any concept of inertia when you are thinking about this framework? So if you think about stimulating a region to achieve a global target state, is there, would you need to take also into account the fact that some pathways in the brain have different delays, and also the fact that if you want to stably reaching this state, you may want to have the stimulation on for some time? Thanks.
Yeah, those are great questions. So you can definitely have different lengths of the control input, different time lengths of the control input that may be important to drive a particular state transition. So that's definitely sort of part of the structure. But your question about inertia and the second question about the time delays are really important and interesting. You can incorporate the time delays in the way that you state the edges, and so that's something that is possible. It's not something that we've done yet. So I think that unless to the degree that time delays are related to the weights that we're already using, but there's conflicting data about that. The last part, which is what you started with about inertia, I think is really interesting. We do think a lot about not just how much energy it takes to transition between two states, but also how much energy it takes to hold a state. And so while some people may have great inertia sticking with a two-back task with, focusing their attention and just continuing to do it, others have brain dynamics and brain structure that seem to support kind of a falling away of certain states. And so we can use this approach to estimate the energy required to just hold a state for a period of time. If that state is not a minimum on the energy landscape, then it requires energy to hold. And we can estimate that using this approach.
Thank you very much.
Thank you indeed. One more question from the audience, and then I'll go over to you, Randy and Susan, on the panel. There's a question here from Luis Colon-Perez and from Dan Lurie. The two of you kind of have the same question, which is really on the nature of perturbation and whether neuromodulation can be considered a perturbation or something related to your concept, Danny. Dan, Luis, if you are out there and can raise your hand, I can see you. Luis, there you are. Go ahead. Oh, sorry. Sorry.
Yes.
Go ahead, Luis.
Hello. Thank you. Thank you for the amazing talk and for the organizers. So my question was related, because it's a lot of the perturbations was related to maybe modifying a particular brain region or section. My case is if you have perturbations of a state basically driven by pharmacological interventions, so it's basically like a drug that maybe attack dopamine or opioid receptors that are not necessarily localized in one area of the brain, is there like an approach that we can start to explore these questions in a dynamical process in network control theory? Thank you.
Yeah, that's a really great question. And I would just point you to the Singleton et al. Paper from 2011. That's from Amy, I'm going to mess up the last name, Kiewski's lab at Cornell. And so that paper is really neat because it's a study of LSD and the effects of LSD. And they do that by by incorporating the regional variation in serotonin 2A receptors across the brain inside the B matrix. So that means that when you have control input being injected, it's going to preferentially go along to some of these regions and not others based on the receptor density. So I think that's a really cool approach and is directly related to your question about drugs, but also about incorporating more of the biology.
Thank you. Yeah, I already took a picture. I was going to read it. Great.
Thank you for the question. Just a note, I'm seeing a question here that's a little bit more general, that has a lot of support behind it. I want to leave that to the end of this segment, but I do want to take it up. So raised by someone in the audience, I'm going to come to that towards the end, but now let's go over to Randy.
Thank you, Olaf, and thank you, Danny. I appreciate the tour of network control theory. I guess one question I have has to do with the nonlinear aspects that you talked about, and how one takes into consideration the fact that there is a sort of an inherent stochastism to nonlinear systems, particularly when you have initial conditions that might change how the trajectories go, even in face of stimulation, and how you can account for that in deriving some of the control parameters for your models.
Yeah, that's a really great question. I think the only way that we've been able to incorporate that a little bit is by using a different A matrix that is more context dependent. So in other words, the brain is in this particular dynamical regime, and based on that dynamical regime, there's this pattern of flow, and then we use that for the control. But I think that there's a lot more work to do here, I think, to take into account the stochasticity. The work that I'm mentioning is from Leah Papadopoulos. It's in PLOS Computational Biology last year, maybe.
Yeah, I mean, it looked like when you gave the examples of the nonlinear modeling, you can sort of define a distribution almost of which encapsulates the possible trajectories that are, I guess, contextually dependent. And the question is if you can expand that. I mean, Victor in his presentation the other day talked about using Markov chain Monte Carlo, for example, to actually identify when you don't really have a complete sampling of the system, you can actually use that to infer these other states that are not possible. So that could be sort of incorporated to allow you to explore that stochasticity a bit more, and then derive sort of a broader model that can account potentially for the initial conditions.
I really like that suggestion. I think that would be a really neat direction to go.
Talk to Victor, he's right here.
Okay. Victor, I'll talk to you.
Great. Over to Susan. Go ahead, Susan.
Hi, Dani. Thank you. So I wanted to know if I could if I could probe you a little bit more about this question of cognitive effort, because it's something we kind of hear a lot about, and there's a significant amount of hand waving that goes on about it. What's cognitively different, and it kind of can also semantically creep into cognitive fatigue, what we think of as being hard, being able to sustain, being on task. What do you think is, and it's a huge problem for many for individuals who have experienced brain injury, that they will say that they suffer from this sense of cognitive fatigue, right? So what do you think is actually going on with this idea of what is cognitive effort, and what is the energy that we're actually utilizing to sustain a state or to transition from states? Is it the traditional kind of metabolic energy that we would think about? Is it energy as information? I mean, could I probe you a little bit to say more about this?
Yeah, definitely. So my understanding of cognitive effort and cognitive fatigue is that there are at least two suggested mechanisms. One is that it's related to the metabolic energy that's being required. And then the second, which I think Nathaniel Dahl is really excited about, is about an opportunity cost. It's costly to make me do something if I'd really rather be doing something else. And so this can feel very taxing and cognitively fatiguing because I want to be doing something different, even though technically the two tasks would be similar in terms of energy consumption. So there's one that's like a motivational driver, and the other one is really a biophysical driver. I think that in this case, the theory more aligns with the energy metabolism version, although Nathaniel and I are talking, and maybe we'll find a way of connecting on the opportunity cost too. I don't know. But we have some data that suggests that the control energy required to go from a 0 back task to a 2 back task is more than the control energy required to go from the 2 back task back down to 0 back. And so that's consistent with our notion of how much cognitive effort's required to go up in complexity in a task than to come down in complexity in a task. So that's a nice, at least preliminary piece of data. The second piece of data, which is not yet on arXiv, but hopefully will be coming soon, is connecting the control energy statistics to energy metabolism using PET imaging. So that I think I'm excited about because it makes it a little bit more grounded in the physiology. But I think that in general, the answer to your question is that we don't yet know. But I think that there's enough promising bits here that lead us to think that we should continue and see where it leads.
Thank you. No, I agree. I think this would be a fascinating area for the science of, to really begin to hone in on, because I think it just has been talked about too vaguely to be really useful. And it's an important problem. So great, terrific. Thank you.
This idea of mental effort relates to cognitive control, which we're actually going to turn to in the talk after the break by Mike Halassa. So an interesting sort of a new take on control, this time from the inside as opposed to in an invasive fashion. There's a few more questions from the audience I want to turn to here. Johan Wards, if you're out there, you had a question on a remark that Dani made in her talk. If you're out there, go ahead and raise your hand so I know where you are and I can hand you the mic. This is, if we were in the real world, we would now be rushing through the lecture hall with a mic in hand and try to hand it over to our colleague, Johan. Where are you? If you're not out there, I'll just read the question real quick. Dani, you made a parenthetical note on mentioned electrical stimulation. Do you think that a non-invasive exogenously applied electrical field could be used to drive the state of a particular network in an individual towards a potentially more desirable state? So can this be used for invasive manipulation of brain states in individuals?
Yeah, that's a really good question. So we have two papers on that topic that use electrocorticography data and stimulation on the grid of the brain surface. And when we apply the control framework, we find two things. One is that if you stimulate a region that has high modal controllability, you tend to push the brain towards states that are associated with better memory encoding. So that's an initial suggestion that yes, you can use brain stimulation and you can target high modal controllers and you can drive this particular beneficial state for an individual. The second piece of data that we have is work from Jenny Stizo. It was published in Cell Reports maybe last year, maybe the year before, I don't remember, which asks, if we use a network control framework and we just do open loop control. So we say, here's the initial state, here's the perturbation, this is where it was stimulated, how the stimulation magnitude, intensity, frequency, etc. Can we predict the future states? And the answer is yes, to some degree, although the prediction accuracy still leaves a lot of variance unexplained. But it's an initial suggestion that the approach is relevant for understanding the effects of stimulation.
Thank you very much. I know Johan appreciated the answer, is responding here, but apparently in a time zone that's must be on the other side of the planet. Right, another question from the audience. Andrea Lupi has another question, not another question, but a question for you, Dani. And there you are. I'm going to unmute you. Go ahead, Andrea.
Hi, thank you for this very illuminating talk, Dr. Bassett. I was just wondering if you have thoughts on how one may summarize an entire fMRI time series, an entire fMRI scan into a particular state that one can then use for control, as opposed to using many different time-resolved states.
Yeah. We are typically studying individual time-resolved states. So for fMRI, you can think of each state as the activation levels estimated in a single TR, right? And so then you can say, as we go from TR1 to TR2, how much energy was required, or from TR2 to TR3, how much energy was required, what was the trajectory? So you can apply it in that sense, TR to TR. Or you can say, let's take an entire task and look at the general linear model of the task activation and say, here's the activation profile for 0 back, here's the activation profile for 2 back, how much energy is required to move from one to the other. And that's relevant for tasks that are making people switch between 0 back and 2 back. So those are two examples. Those are more, data motivated, which I really like. We also started with something that's very non-data motivated, which is just to say, let's come up with random states and ask, can the brain, how much activity or energy would the brain need to get between these random states? And what is the common target state that any random state can get to with very little energy? And it turns out that that target state that any random state can get to with little energy is activation of the structural core set of nodes, like areas that are similar to those in the default mode system. So that's a little interesting tidbit, might be relevant for you.
Thank you.
Very cool, very interesting. I have another question here from Genji Kawakita. If you're out there, Genji, and would like to raise your hand, go ahead. There you are. Thank you. Go ahead, Genji.
Thank you for a great talk. So this year's workshop's main theme is consciousness and cognition. So I would like to hear your opinion on how we can utilize network control theory to, for example, transition from unconscious brain state to conscious brain state?
That's a really good question, and I will just have to say that I haven't done any work in that space, so I'm not the person to ask, I think.
Would someone else on the panel who maybe has thoughts on consciousness chime in? After all, we can talk amongst each other, right? Anybody else out there? How could you, maybe a broader question, how could you connect the control theory framework to transitions between levels or states of consciousness of the kind we've just discussed? Anybody out there have a thought on that?
I'll briefly say that I think that's definitely a case where you're going to need at least the linear time varying model, because the states of consciousness and unconsciousness are so different that I don't think that would make a lot of sense from the linear perspective.
Yeah.
But you may also need to move to the nonlinear models as well.
Okay, I briefly confused myself, but there's another question coming in right now that I think would be good to go to next. From EA Cambridge 2, I don't know, that's a person I imagine, EA Cambridge 2, if you're out there, EA, go ahead and ask your question, otherwise I'll read it off. I'll read it off real quick. The question is about, has there been any work relating controllability to brain development, including neurotypical and atypical?
Yeah, I'm so glad you asked. There is a lot of work in that space that I'm really excited about, and some of my colleagues are too. So we definitely can tell that network controllability statistics, like the average and modal controllability, increase with development as we go from 8 years to 22 years of age. So that suggests that there's an increasing capacity to enact state transitions with lower energy. So that's neat. There's also some beautiful work from Jiaju Q, who was a postdoc in Ted Satterthwaite's group and is now a faculty member in China. And he showed that the energy required to transition the brain to activate the frontal parietal system, which is typically associated with executive functions and cognitive control, that energy varies a lot across individuals and decreases with age. So as people move from 8 to 22, they require less energy to activate the frontal parietal cortex. And that's consistent with the notion that these individuals also are able to engage in executive functions more easily. Relatedly, individual variation in that effect is correlated with individual differences in executive function on a large cognitive battery. So again, in the direction that makes sense, so lower control energy required for that transition is related to greater performance. So suggesting that when these transitions are easier, people perform better. And that changes over development. Oh, and then non-normative development. Lyndon Parks has a paper that just came out in Biological Psychiatry, or it's in Press in Biological Psychiatry. I think you can find it on medRxiv. And he shows that psychosis positive symptoms can be predicted significantly by controllability in transmodal cortex. And that's in youth, again, from 8 to 22, but psychosis positive symptoms in those youth. So those are a few examples.
Great, that question was right on. There's another question here from Andrew Lin, a question really about, paraphrasing, how do we get started applying neural control theory? Andrew, if you're out there, would you like to flesh that out a little and ask your question? Please raise your hand. There you are. Go ahead, Andrew.
Hi, Danny. Thanks again for a great talk. I see a lot of the sort of questions that you're answering in much different systems, sort of paralleled in sort of what I'm thinking about with academic achievement and child development, and sort of what brain states, kids might be able to get to, and how that transition between brain states might underlie, higher performers. So I have obviously some background in connectivity and stuff, but I definitely think that this is the next level for me. So I was just wondering if you could just point us novices into a book or a couple of reviews that might be helpful in breaking down some of these really complex topics that you did so well in only 20 minutes. Thanks.
Sure, yeah, I would be really happy to. Maybe what makes sense is that I think I have access to the Q&A box, so I could put a couple resources in there. And also, if you can't get them from there, or for some reason it doesn't work out, feel free to send me an email, and I can also send a bunch that way too.
Great, thanks so much for your help.
Sure.
That's a good point.
We also have all the tools on GitHub freely available, so everybody can use them.
I was going to ask about a toolbox. I know you have one out there, and that's always a good stepping stone as well. I want to turn to this question that perhaps also you can see, Danny. You can see the Q&A box, which is a general question, but I think one that is worth talking about. The question about the transition in fields, coming from a, let's say, more clinical perspective, going to the type of math and modeling that we have been discussing here for the last day and a half. And I know it's a question often asked. Also, I get questions like this often in email and so forth. So maybe worth addressing. Dani, you are of course free to address it. Anybody on the panel as well. The anonymous attendee who asked the question, if you're out there and want to raise this point yourself, please go ahead and raise your hand. Watching the I'm watching my chat box here. I don't see it. So let's just generally pose the issue. You know, this community, brain connectivity, has been interdisciplinary from the beginning. You know, and it started kind of with a very small group of individuals getting together, talking about applying things like, you know, dynamical systems and graph theory, et cetera, to the brain, which was, you know, not at all middle of the road or mainstream 20, 25 years ago. But there's still training issues of how do we learn about this stuff? How do we learn about using it properly? How do we get started? What are your thoughts, Dani, on this? And then others perhaps who want to chime in as well. I know you've thought about this quite a lot,
yeah,
Dani, and so yeah.
Yeah, I think there are a couple things. I'm really excited about just developing more theoretical neuroscience graduate programs that would combine education in neuroscience and education in the physics and mathematics. But that's a long-term goal. So I think something that may be more proximal to you, Anonymous, is that I think that I've found most exciting actually working with somebody who has a lot of expertise in that area. So I still work really closely with Fabio Pasqualetti, who's a control theorist that has typically thought about power grids and robotics and things like that. I learned so much from him. And he also makes sure that I don't apply something in a stupid way. So I really enjoy that. It makes it more social, makes it more fun. So I would recommend that. Although I know that there are many differences in personality, and some people really just want to dig in themselves and learn it all from scratch. And I completely support that too. I'm just sharing that from a personal standpoint. It's a lot of fun to work with other people who have more expertise in that space.
Any other thoughts from other panel members?
Yeah, I can underscore that. I mean, John Griffiths actually posted a link to the INCF training portal, which has a lot of courses, actually online courses that are helpful. But I too agree with Dan. It's not really, you learn best by doing, really. And by doing, you actually, if you have someone to kind of give you the parameters within which you want to work, and you say don't do something stupid, that really helps a lot. And you know, in some respects, you know, I'm kind of tooting my own horn in the sense of what we've done with Brain Connectivity Workshop is actually brought people together who span those domains. Like the people in the attendees group, even the people in the panel, don't all have the same expertise. But I think by having these discussions that are sort of, you know, unstructured, it helps us sort of dig out some of the key issues and then find ways to help solve them together. And I've benefited tremendously by working with Victor and Petra, for example, on building the virtual brain, because each of us has our own expertise and can sort of guide one another to being successful. It's hard to do, but I think it's also worthwhile doing if you have the opportunity to do that, even if for a couple of months, it's worthwhile.
Susan, you have a thought as well.
Yeah, thanks, Olaf. Yeah, I think I agree with what Randy and Dani have said. I mean, I think part of the difficulty is that you also have to be starting at a particular place. I mean, everyone has to bring something to the table if people are working together on a problem. And I think particularly the questioner asked about things like, you know, clinical situations. The problem is that so much of clinical science and preclinical work is really a mathematic. You know, it is. And so the mathematical skill set, the mathematical basis for many people in the fields is actually quite low. And so I think we also have to get serious. And I know, Dani, this is another like long-term problem, but I think we have to get serious about the way that we increase the exposure to these kinds of tools and thinking into mathematics in both, you know, undergraduate work, graduate school, and for people who are going into professional training, because this is unfortunately where the world is moving. I mean, we need to be able to ask these kinds of questions. But in the meantime, I think we do need more things like this. I mean, I think the education day yesterday, you know, could serve as that kind where people could bring particular problems, and people could begin to, show how you might begin to think at it and work at it. But I don't think it's an easy solution, because I think some of us who are old enough have seen what happens when people just borrow and steal tools from somebody and start throwing everything at the wall, hoping it'll stick like spaghetti. So, I mean, I think, it really takes commitment, it takes compassion and the willingness to both share and to learn. And I think it's something we have to take very, very seriously if those of us who believe that these kinds of approaches are the way that we're going to solve very difficult and intractable, seemingly intractable problems. Thanks.
I think these are all very, Carl, are you out there? You raised your hand. Go ahead, Carl.
Yeah, no, I'm here.
You're here. Great to see you.
It's lovely to see you. No, I just wanted to endorse Susan's point and also Dani's point about this, the importance of foundational training. I mean, I take a very strong position that if you want to make a difference and use these tools wisely and indeed develop these tools, you're going to have the right foundational training. And it did strike me, and Susan said this, of course, yesterday was a lovely example of offering that kind of, of training. The point, though, I wanted to make is it's a shame that Michael Breakspear isn't here, because he got very upset about 2, possibly even 5 years ago now, because he and a lot of you put a lot of energy into the educational courses for the OHBM, specifically to raise the bar and to offer a whole day of introductory maths and dynamical systems theory and analytic tools, exactly along the lines of what we've been talking about today. And yet he was asked to withdraw that, and he couldn't understand why. It may be that part of reinstantiating that, which I think is necessary. I think everybody appreciates that in every field, whether it's sort of computational psychiatry through to the virtual brain project. One way to I think rebalance that is to for people on the ground, for people in the audience, for example, for the next generation of people who are deciding what do I need to learn and how am I going to access that learning, to put pressure on the people who decide what courses to accept and not accept. And indeed, at the end of this meeting, it will probably degrade into a discussion of what we got right and what we got wrong. And that's a very useful thing, because we should be taking on board what the next generation needs to know about. But I'm really speaking for Michael. If there's anybody out there thinking that everybody should know about the most recent scientific tools available and the mathematical basis, then you should email the educational subcommittee and representative on the OHBM and just tell them this is what we actually need.
Very good thought, Carl. I have myself taught in the OHBM educational program a few times and know how important that is. And I will also say that just to round out this discussion, that it's also important to allow these ideas that we're articulating here in this workshop and have articulated for the last quarter century to get out there and to blossom and to be criticized and to get peer reviewed and to get published. And that was terribly hard in the old days. It almost killed my career in the 90s when I started working on this stuff, and there was no way forward. I hope it's gotten a little better. And on a somewhat selfish note, I'll say that we now have at least one journal, Network Neuroscience, that is devoted to the intersection of networks and connectivity in the brain, and is doing very well, an open access journal published with MIT Press. And I wish that journal was around when I was a little younger and a little bit earlier in my career. And I hope that it's providing a service to the community and to the field at large. If you are interested in learning more about it, please do look it up. We are right at the almost 4 o'clock mark. I'm going to suggest that we thank Dani for a really stimulating discussion and presentation. That was fabulous. We've had a really good 3-hour stretch.